Welcome to Math 310, Introduction to Modern Algebra. This is lecture 9. So we're going to talk today about subgroups, homomorphisms, and continue to do some of the applications of the material we've been seeing. So we ended the last class by talking about what is a group homomorphism. So we have two groups, G and G prime, and we have some map phi from G to G prime that is nice. And what do we mean by nice? It means that if you look at phi, oops, I'm at super large size. If you look at phi of G1 dotted with G2, and I'll put a little subscript G to remind us that this is the composition rule with respect to the group G, then this is phi of G1 composed with, and I'll do a G prime here, phi of G2. So things are as nice as possible. It doesn't matter which order you do things. I can combine G1 and G2 and then apply phi, or I can apply phi and then combine the result. So it's really nice when you have things when the order doesn't matter. So last time we showed that the identity element is unique. And then what we want to do today is we want to show that if G is some element, that the inverse of G under phi is exactly what you would expect. It's phi of G inverse. Okay, so all of these proofs proceed very similarly. Yeah, for the last one, it was like, what elements do we know? Well, we know we have the element E, the identity. That's what we had to work with. So over here, what do we know? So for B, we know we have the elements E, E prime, some element G, and some element G inverse. Those are the elements we know. It's actually a lot easier to prove something like B because we have a very natural guess to check. And all we have to do is check and see if it works. So what does it mean to be an inverse? We have to go left side and right side. So we'll just do one. Do you want to do left side or right side? Does it matter? Which one? This is one of the easiest questions I can ask. This is who's awake, left or right? Left, there you go. So we'll do left. So what is phi of G inverse times phi of G? That's phi of G inverse G by definition of phi, because phi is a group homomorphism. But what is G inverse times G? E. It's the identity element on the group G, as G inverse is the inverse of G. And then what is phi of E? E prime by part A. Thus, phi of G inverse is the left inverse of phi of G. Okay? And then you would do the right-hand side similarly. Or what are you strongly urged to prove? If you have a left identity, then you also have the right identity, and it's the same element. If you were to just prove that, then every time we get a result like this, we wouldn't have to do both cases. So I strongly urge you prove that at some point. Okay. So two groups, G1 and G2, are said to be isomorphic if there's a bijective homomorphism. So bijective means one-to-one. Sometimes people say injective. And onto, and sometimes people say surjective. So what does it mean to be one-to-one? It means I can't have two elements being mapped to the same thing. What does it mean to be onto? It means everything is hit. How many of you have not seen this notation before? Okay. And so if you're both one-to-one and onto, then we say you're bijective. And in fact, in this case, you also have an inverse. Because every element is mapped to something unique, and everything is hit, you can just run the map backwards. So if A is sent to B, then your inverse map is going to send B to A. And because it's onto everything is hit, so you will have a map defined on G2. And since it's one-to-one, it will always go back to something unique. Okay, so two groups are said to be isomorphic if there's a bijective homomorphism between them. It's an isomorphism. Okay. So the math is called an isomorphism. So isomorphic groups are essentially the same group, but their elements have been given different names. You have hopefully seen this several times. If you look at things just the right way, you realize, oh, okay, I know what this is. I think I showed you a Rubik's Cube where it looked different, but if you held it at a 30-degree angle, you then realize, oh, it's the same as a normal cube with pictures on the side. If I just make these identifications in my mind, it's going to be the same. So sometimes the way information is given, it's a little bit more natural. It's a little bit easier to study something with one formulation than another. And so the whole point of this is that if I can prove these two groups are isomorphic, then anything I prove for one, I now know for another. So let's try to think of maybe two groups that might be isomorphic. So let's look at Z mod 7Z star. This is going to be the numbers 1, 2, 3, 4, 5, 6 under clock multiplication with 7 as the number of hours. Okay. So for example, what would 3 times 4 equal on a clock with 7 hours? 5. 3 times 4 is 5 more than 7. What would 3 inverse be? What do I have to multiply 3 by to get 1? So we know it's not going to be 4. We know it's not going to be 1. 3 times 2 is 6. 3 times 3 is 9. 3 times 4, we just did. 3 times 5 is 15, which is 1 more than 14. So 3 inverse is going to just be 5. Okay. Let's let zeta 7. Let's do zeta 6. Is going to be e to the 2 pi I over 6. Okay. What's the square of that going to be? That'll just be e to the 2 pi I. I'm going to write it as 2 over 6. Zeta 6 cubed is going to be e to the 2 pi I 3 over 6. And what's zeta 6 to the 6 going to be? So if I raise e to the 2 pi I over 6 to the 6th power, what do I get? E to the 2 pi I. What's e to the 2 pi I? Has everybody seen e to the 2 pi I? Okay, so what would e to the 2 pi I equal? This is cosine 2 pi plus I sine 2 pi. So what would e to the 2 pi equal? What's cosine of 2 pi? 1. Draw the unit circle, right? Here's the unit circle. If I give you the angle of 1, 0 or 2 pi, I'm at this point. The cosine is going to be 1. What's the sine of 2 pi going to be? 0. So zeta of 6 to the 6th power is 1. This is a cyclic group. right? So it's generated by zeta of 6. What do you notice about this cyclic group and Z mod 7Z star? What do they both have in common? They both have 6 elements. So maybe we could come up with a homomorphism, a group homomorphism from one to the other. What's nice is because this is a cyclic group, once I figure out what phi does to zeta of 6, I know what it does to everything. So I just have to figure out, what do I send zeta of 6 to? Is Z mod 7Z star cyclic? Is that generated by the powers of one element? Could it be generated by powers of 1? No, right? What happens is you keep raising 1 to its powers. 1 times 1 is, times 1 is, times 1 is. Okay, 1 is not going to generate it. What about 2? 2 times 2? 4. 4 times 2? And 8 is the same as 1, so it's not generated by 2. 3, however, 3 times 3 is 9, which is 2. 2 times 3 is 6. 6 times 3 is 18, which is the same as 4. 4 times 3 is 12, which is the same as 5. 5 times 3 is 15, which is the same as 1. It is generated by 3. So this is cyclic generated by 3. Does anything else generate it? We know 1 doesn't, we know 2 doesn't, we know 3 doesn't. Since 2 doesn't, could 4 generate? What about 5? Five times 5 is 25, which is the same as 4. 5 times 4 is 20, which is the same as 6. That's already enough to show that it's not an element of order 3. It's not an element of order 2. So the next possibility is it has to be an element of order 6. So it is also generated by 5. You could check that. So we have a couple of possibilities. I have 2 generators here. You could ask if I have any other generators down here. And so I strongly urge you to go through and try to figure out, can you construct a group homomorphism between these two? Can you construct a group isomorphism? So a group homomorphism doesn't have to be onto. All you have to do is you just have to have, phi of G1 times G2 is phi of G1 times phi of G2. I want something stronger. I want something which is 1-to-1 and onto. Can you give me a natural candidate to try? Try phi of zeta of 6 equals what? Would be a good thing to try if you want a group isomorphism. I know Z mod 7Z star is cyclic, generated by 3 and 5. I know this group is cyclic, generated by zeta of 6. What should I try sending zeta of 6 to? Right. How many possibilities do we have to send it to? I don't care about the right one right now. How many possibilities? How many options do I have? I have 6 options, right? So there's not that many things to try. What would be a good thing to try if I wanted to try to be an isomorphism? We have 6 possibilities. You want to make sure you get everything. What would be a bad thing to try? That's not going to lead to getting everything. Which constant? Well, whatever you give it, that's what it's being sent to. Which number from 1 to 6 would be very bad if you want to try to get everything? 1. If you send zeta of 6 to 1, then everything is sent to 1. So would that be a group homomorphism if we send everything to 1? What's the definition? Is phi of G1 times G2 the same as phi of G1 times phi of G2? If everything is sent to 1, is phi of a product the product of the phis? If everything is sent to 1. If everything is sent to 1, then what's phi of the product? 1. If everything is sent to 1, that's 1, that's 1, their product is 1. If you send everything to 1, is this a group homomorphism? I'm not saying isomorphism, I'm just saying, is it a group homomorphism? All you have to be a group homomorphism is phi of the product is the product of the phis. If everything is sent to 1, does this always hold? Yes. This will be a group homomorphism. It's not going to be useful, but it will be a group homomorphism. So I could send everything to 1, but there's no way that's going to be an isomorphism. There's no way it's going to be surjective. I'm not going to get everything. What would be a good candidate to try to send zeta of 6 to? 3. And what would be another good candidate? So we could try 3 or 5. What if we tried sending it to 2? Oops. As another possibility, we could try sending it to 2. And so go home and do the calculations and see, would this be a group homomorphism if we send zeta of 6 to 2? And you would need to check to see, is phi of a product the product of the phis? How many things are there to check? How many products? So how many things do you have to check? Why 6?
Oh, no.
So we have 6 elements, so how many products are there to check? I'm going to start calling on people randomly. How many products are there to check? I don't want to keep hearing the same voices. You have 6 elements. How many products can you form? How many choices do you have for the first element? 6. How many choices do you have for the second element? 6. So how many products are there? Why 6 to the 6th? We have 6 choices for the first, 6 choices for the second. So how many pairs are there? I've got to choose 2 elements for my product. So if I have 6 choices for the first and 6 choices for my second, how many would that be? So it's not 6 to the 6, you're close. What would it be? We have 6 for the first spot, 6 for the second. So how many pairs do we have? 30. Well, that's not pleasant, but it's not horrible. You could do 36, but we can do it a little bit better. What do you know about this product? What additional property does this group have? Not every group has this property, but it's a nice, it's commutative. So because it's commutative, we have 6 choose 2 ways to choose 2 distinct elements, plus 6 choose 1 way to choose the same element twice. 6 choose 2 is 6 times 5 over 2 is 15, plus 6 is 21. So if you use the fact that it's commutative, you can actually reduce it to just 21 things to try. The other thing we can do is, we're looking at the cyclic group generated by zeta of 6. So zeta of 6 is e to the 2 pi I over 6. So any element here is of the form zeta of 6 to the 6. So if I want to look at phi of 2 elements, let's say G1, G2, that'd be phi of zeta 6 to K1, zeta 6 to K2. Okay. And so I just have to figure out what happens, and does this equal phi of zeta 6 to the k1, phi of zeta 6 to the k2. And here is something useful to prove. Prove if phi is a group homomorphism, then phi of g to the k is phi of g to the k. If that were true, that makes this problem a lot easier. Because once I know what phi does to the generator, then if I raise the generator to a high power, well, that's just phi applied to the generator raised to the k. So if that were the case, then this problem would be immediate, right? So is phi of g to the k equal to phi g to the k? Can anybody give me a value of k where this is easy? 1. If k equals 1, it's trivial. Building on that success, what's the next value of k? 2. If k equals 2, then phi of g squared is phi of g times g, which is phi of g, phi of g, which is phi of g, whole thing here. In this step, why is that step? Why is phi of g times g phi of g times phi of g? Because okay, I would have done g squared times g, but it doesn't matter. So you said g times g squared? It's phi of g times g squared, which is phi of g squared because it's a group homomorphism. I would like this so I can have the arrow pointing down as well. But what is phi of g squared? Phi of g times phi of g. And that gets us phi of g cubed. How should we do this in general? We don't want to spend the rest of our life doing higher and higher k. How should we do this in general? What method of proof? No. Induction. So what I hope you can see from this is that sometimes when you're doing a problem, it's better to stop, think, what can make this helpful? What can be of assistance in this problem, which I might be able to use in other things as well. So over here, when we were trying to analyze what's going on, I can go from 36 multiplications down to 21. That's still a lot to do. But now I've reduced it to, hey, I know if I take the generator to the kth power and apply phi, that's the same as applying phi to the generator and then raising it to the kth power. So I can make these calculations a lot easier. And now instead of having to check everything, it's going to be really fast. And so it's often worthwhile to stop and think, can you isolate something that will be of use in the future problems? Okay, so again, I urge you to go through, put in all the details, make this work, prove this rigorously by induction. It's good to have some practice proving things like this. This is a very classic technique of just grouping things. And then it allows us to just fill in the proof by using early results. Okay. So isomorphic groups have identical structural properties. For example, if G1 and G2 are isomorphic, then here's some things that are in common. So the idea is if I know things are true about one group, then a lot of that should be true about another group. So it would be shocking if two groups were isomorphic and they had different sizes. Isomorphic groups are supposed to be essentially the same, so they shouldn't have a different number of elements. If things are commutative in one of them, then it should be commutative in the other one. And so I'm not going to go through and you prove all of these, we only have so much time, you should make sure you understand the proofs. You should go and try to prove some of these. If you have any trouble, please let me know. Things like this would be great exam questions. These would be great homework questions. The idea is you want to break the study of a new object into something you already know. Okay, so how could you prove that groups are not isomorphic? So one way you prove groups are isomorphic is you construct a group homomorphism between them that's injective and onto. You construct this bijective group homomorphism. And if I can do that, great, they're isomorphic. What if I can't do that? Maybe I'm just not being clever enough. Maybe I'm not looking at it the right way. Just because I didn't find something doesn't mean somebody else might find it. And there have been times like that in mathematics where professional mathematicians have actually missed certain constructions, especially in tiling theory. And just amateurs have just said, well, what about the following? Yeah, that works. Yeah, okay, yep. So just because you haven't seen something doesn't mean that it's not there. So does anybody have any idea of how we can prove two groups are not isomorphic?
You find an element in one that's not in the element of other, or
what do you mean by not in? Because
oh,
again, what we were doing a few moments ago, they have no elements in common. But it turns out the element 3 could act like the element zeta of 6.
right.
So think Chekhov's gun. How could you show two groups are not isomorphic?
Find the contradiction among those.
Yeah, so be explicit. Give me a specific thing.
Check if one is finite, if they're both finite.
Okay, so what if they're both finite?
Next one.
Well, you're almost there. So more than just checking to see if they're both finite, what should I look at? If I want to show that they're not isomorphic. How many elements does the first group have? N. And what would allow you to show that it's not isomorphic to the second group? The first group has n elements. If the second group doesn't have n, right? So if I want to show two groups are not isomorphic, if I show they have different number of elements, then they can't be isomorphic. So we have a list of isomorphic groups have identical structural properties. So if we can show that one of these properties holds in one but not the other, they can't be isomorphic. If one of them is abelian and the other one is not abelian, then they can't be isomorphic. If one of them has an element of order n and the other doesn't, they can't be isomorphic. So, for example, let's look at the first group G will be 1, 2, 3, 4 clock multiplication 5 hours. And group 2 will be 1, 5, 7, 11 clock multiplication 12 hours. Is it possible that they're isomorphic? Is there at least a chance? Okay, good. Why is there at least a chance? They have the same number of elements. Is that enough to conclude? Maybe. You don't know enough to say no, right? It seems quite unlikely that every group with the same number of elements is isomorphic to any other group with that number of elements. But it's possible. We haven't done that yet. So let's try to figure out some things about the structure. Are these groups commutative? Yes. So we can't use that to eliminate. Now, does anybody remember what the inverse of 5 is on a clock with 12 hours? It's up. And 7. And 11. It's up. So every element is of order 2. So all elements are of order 2. But in G1, we go 1, 3, 3 squared. What is 3 squared mod 5? 4. And then 3 cubed is 27, or it's the same as 4 times 3, which is 12. What's 12 mod 5? 2. And then 3 to the 4th is 81. What's 81 mod 5? It's 1. So G1 has an element of order 4 is cyclic, not isomorphic. So G2 has no elements of order 4. G2 is not cyclic. So we've just shown that these two groups are not isomorphic. There's going to be no way that we can find a isomorphism between the two groups. Can we find a group homomorphism between G1 and G2? Your life depends on it. Can you find a group homomorphism? Yes. What would you do? Send everything to 1, right? We can always do that. So we can always find a group homomorphism, but we can't always find an isomorphism. So not everything is the same as everything else. All right, so in the textbook, they have a really nice box, 3 steps to analyze mathematical objects. The first is deconstruction. Break your object into smaller and simpler pieces. Step 2, analysis. Once you break them up, analyze them. And then step 3, put them back together. So rather than doing a very complicated problem, break it up into a lot of smaller, simpler problems. Okay, this is really good advice. I would much rather do a lot of easy things than one very hard thing. And a lot of times with the easy things, you don't have to go as far. So it's a lot easier to think, what should I try to do next? Whereas when you try to do it all at once, it can be oftentimes daunting. Okay, so we've talked a little bit about what is a subgroup, just restoring the slide. A subgroup is basically a set of elements in a group that is a group under the same operation. So a lot of the properties were trivial. It has to have the identity. Associativity you inherit. Every element has an inverse, but you don't necessarily have the inverse in your subset. So in order to be a subgroup, it must contain all the inverses. And then it must be closed. So we know if we multiply any two things in H, it's going to be something in G, just from the definition of the composition law, but it doesn't have to be in the subset. So if it is in the subset and the inverses are in the subset, then we say it is a subgroup. And I asked you before, what is the linear algebra equivalent? Subspaces. So you could have a vector space and you could have a subspace living inside the vector space. And so if I'm in 3-dimensional space, can somebody give me a subspace in 3-dimensional space?
Any 2D plane going through the origin.
Excellent. Any 2D plane going through the origin. I don't have enough money to afford a 2-dimensional subspace. I'm on a really limited budget here. I can afford a 1-dimensional subspace. What can you give me? I want a 1-dimensional subspace in a 3-dimensional world. So you give me a 2-dimensional plane going through the origin.
Just the line going through the origin.
Just a line going through the origin. So I can have subspaces of different dimensions. Similarly, I can have groups of different sizes. I can have subgroups of different sizes. Okay, so let D be some integer. We can form a subgroup of the integers by just looking at the multiples of D. And clearly, under addition, a multiple of D plus a multiple of D is a multiple of D. Associativity is fine. What's the identity element under addition? 0. I'm going to have 0. So the only thing is the inverse. What's the inverse of M under addition? Negative M. And so over here, instead of taking, if I have the element Dn, its inverse would be negative dn, or d times negative n, so we'll have the inverses. So this is a subgroup. So can I construct a group homomorphism? Can I find a map C from the integers to dz that is a group homomorphism? And now everybody should be yelling out the answer. Yes. Why can I find such a phi? What? Phi of n equals 0. Find a non-trivial one. So the question is, would there be a non-trivial one? There's a natural guess. What might you try to guess? I want to try to send things to multiples of d. So whatever the output is, it has to be in dz, which means it has to be multiple of d. So if I give you m, what might be a natural thing to try to send it to? I'm sorry? dm. So that's an excellent guess. It's going to force everything to be in dz. If I gave you phi of m1 plus m2, that's going to be dm1 plus m2. That's going to be dm1 plus dm2, which is going to be phi of m1 plus phi of m2. Things are looking really good. Phi of the sum is the sum of the phis. So I'll let you, fill in the rest of the detail. Does this really seem like an exciting map? Does furlongs per fortnight mean anything to anyone? Does anybody know at least what it's measuring? What?
2 weeks.
Furlong, okay, fortnight is 2 weeks, yes, and a furlong? It's a distance. I think some construction projects can be measured in furlongs per fortnight in terms of how much progress is being made. It might be 1/8 of a mile, I'm not sure. It's a horrible unit. But it's a unit of speed. What would you typically use for speed? Meters per second, miles per hour, kilometers per hour. Probably not too many of us will use feet per second. In football, how do we measure distance? Yards, right? We're not in Canada. We use yards. Could I use feet instead? If I change measuring everything in feet to yards or yards to feet, does it change the physical football field? Would it change the play of the game? Hopefully not. Hopefully saying, it's 4th and, 1 yard would not feel differently than saying it's 4th and 3 feet. It makes no difference. I can convert from yards to feet, feet to yards by either multiplying by 3 or dividing by 3. Essentially, that's all I'm really doing here with your map. Is instead of measuring things, if d equals 3, instead of measuring things in yards, I'm now measuring things in feet. So this would be a non-trivial group homomorphism. It's not very exciting, but it shows you that these sets really are the same if I just change my identifications. Okay. We've talked a lot about cyclic groups, groups generated by just one element. And we did some more examples of that today. Cyclic groups are very nice. And if it's cyclic, then any element is of the form UTN. And so if I and so rather than doing painful multiplication, I can do addition. And so we saw an example of this with we had the set, 1, 2, 3, 4, 5, 6. And the group generated by zeta of 6 with, zeta of 6 e to the 2 pi I over 6. If I want to do 3 times 5, I got to multiply 3 and 5, and then I have to reduce this mod 7. If I take things on the right-hand side, if I take zeta 6 squared, zeta 6 to the 4th, that's just zeta 6 to the 5th. I just add the exponents. Which would you rather be doing? Multiplication and then reduction, or just adding exponents? I'd much rather add exponents. So what this is really saying is that this group is really the same as maybe a nice cyclic additive group. And every time you get to 6, you just get to 0. So the whole point is to try to come up with easier ways to do calculations. Okay, so phi is going to be a map from G to G prime. I do not believe there is any time in the book when you have a mapping between two groups denoted by phi and it is not a group homomorphism. You should still say explicitly every single time, but your good notation, you should always be using a consistent letter, a consistent naming convention. If I know it's going to be a group homomorphism, I'll use the letter phi. If I'm not sure, maybe I'll use the letter F. It's some map between the two. So whenever I write phi, it's probably going to be a group homomorphism. If you are doing calculus and you have a little f and a big F, what's the relation? Almost surely. If you have a little f and a big F in a calculus problem. Yeah, derivative and integral. Big F is the antiderivative of little f is the derivative of big F. It doesn't have to be, but this is good notation. You can quickly glance down and see what's going on. So we're not going to use phi as a map between two groups unless it's a group homomorphism. So the kernel of phi is the set of all elements of G that are sent to the identity element of G prime. So let's draw a picture. So here is G. Here is G prime. It has some element E prime. And you know G has some element E. Can you give me something in G that's sent to the identity in G prime? Yeah, we know there's at least one element. But maybe there's other elements. And maybe these ones are also sent. And what we're saying is the set of elements that are sent to the identity element, we're going to call that the kernel of phi. So the kernel of phi, where does that live? Does it live in G, G prime, or neither? Where does the kernel of phi live? It's G. It's all elements in G that are sent to the identity G prime under phi. So this is a subset of G. Instead of a group, what's the natural question to ask?
Is it the subgroup?
Is it a subgroup? So let's do this as a theorem. Kernel of P is a subgroup of P. So we need to show a bunch of things. So the first thing is, do we have the identity? So one, we have identity. As we know, phi of E is E prime. We need closure. If G1 and G2 are in the kernel of phi, then phi of G1 equals E prime equals phi of G2. That's what it means to have two elements that are in the kernel. Each one is sent to the identity. Now we have to check and see what happens to their product. Then phi of G1, G2 is phi of G1, phi of G2. Why is that the case? It's a group homomorphism. But each one of these is the identity. This was by assumption. And what's the identity times the identity? It's the identity. So we have closure. Because they're sent to the identity, their product is also the identity. What's the last thing we need to check? We showed the identities there. Associativity is free. What's the last thing we need to check? Inverse. So if G is in the kernel of phi, must show G inverse is in the kernel of phi. So what would be a good expression to look at? I need a relation involving G and G inverse. So what can I start off with? What do I know? So what relation do I have between G and G inverse? Yes. Excellent. So we know G, whoa, that's kind of funky. Yeah. G times G inverse is the identity. We'll leave it like that because it's so important. What should we do to both sides? So we're starting off with the relationship we know between G and G inverse. What are we given? We have some group homomorphism between G and G prime. And the kernel phi is all the things that are sent to the identity. And so we know that G is in the kernel of phi. So what would be a good thing to try to do to both sides? I've got to do something, right? What do I have left to play with that I haven't used yet? What's the only thing on that first line that I haven't used yet? The kernel of what? The kernel of phi. What should I use? So how's the kernel of phi defined? It's all things sent to the identity by the map phi. So what should I use? What should I apply to both sides? Phi, it's the only thing I have left to play with. So again, I'm trying to emphasize, what do we have to work with in problems like this? You know, if we're trying to show that G inverse is in the kernel of phi, well, what kind of relations do we have? Well, I know G inverse is the identity. But G is not a random element. G is in the kernel of phi. It's sent to the identity. So I somehow probably want to apply phi. Look at phi of G inverse. That's going to be phi of E. Well, what's phi of a product? The product of phi. So this is going to be phi of G, phi of G inverse. And what is phi of E? E prime. And so this is property. And this is group homomorphism. So what do we know about phi of G? What's true about phi of G? It's the identity. Which identity? E prime. So you get E prime times phi of G inverse equals E prime. Well, what's E prime times anything? Itself. So therefore, we get phi of G inverse is E prime. Therefore, G inverse is in the kernel of E. So the proof almost writes itself if you know how to start thinking about it. I start off with, I've got G is in the kernel of phi, so that means G times G inverse equals E. I'm trying to show that G inverse is in the kernel of phi. What do I know about G inverse? I know G times G inverse is E. That's what I know. It's what can I extract from the givens? I'm told G is in the kernel of phi. So I know phi of G is the identity. I want to get a phi of G. How do I get a phi of G? I have to apply the map phi. So let me apply the map phi. And then phi of the product is the product of the phis. And then everything follows from this. Okay. So if we have a group homomorphism between G and G prime, the kernel of phi is a subgroup of G. We just proved that, in fact, right? So the first half of proposition 2.44 we just did. The next one is phi is injective if and only if the kernel of phi is the identity. Well, if you go back and look at the picture before, injective means two distinct elements go to a distinct element. So if there's more than one element that goes to E prime, there's no way it can be injective. So it's a necessary condition that the only thing in the kernel is E. If there are more things in the kernel than E, it can't be injective because all those things go to the same thing. It's not necessarily sufficient. Do you know a necessary condition to win the Super Bowl? Necessary. Every team that has won the Super Bowl, this is true. Yes. Nope. Oh, well, okay. That is yes, but that's not the one I want. I want a weaker condition. Sure. Basically, you play in the Super Bowl. Right. If you do not play in the Super Bowl, you are not going to win the Super Bowl. That is a necessary condition, but it's not a sufficient condition. Ask any fan of the Buffalo Bills. Okay. Now, can you give me a necessary and sufficient condition? Yours will work for this. Score more points than your opponents. That will guarantee that you win the Super Bowl. Okay. So we just showed that it's necessary that the only thing that's sent to E prime is E if you want to have a chance of being injective. But that might not be enough. So what this proposition is saying is that actually is enough. That if you have the kernel is the identity, then you must be injective. You must be one-to-one. It didn't have to be that way, but it goes in both directions. So I will leave that as an exercise for you to prove. If there's some time at the end of today, we'll come back and we'll discuss that. Okay, so we've talked a little bit about subgroups before. What we're going to do now is we're going to talk about cosets, and this is going to lead to Lagrange's theorem, which is going to lead to Fermat's little theorem, which is going to lead to some great results in cryptography and one of the strangest math results I know. I'm going to be able to do something that seems very surprising by the end of class today. So let G be a group, and H is going to be a subgroup. Why do you think we use H for subgroup? Subgroup doesn't have an H in it. Why would we?
After G.
Yes, after G, right? So if I use the letter H, it's almost surely going to be a subgroup. You still have to put in subgroup. If I'm not sure what it is, maybe I'll use the letter S for set or subset. So for every G in G, we can construct the left coset by taking everything in H and multiplying on the left by G. For example, if H equals the identity H1, H2, H3, then GH is going to just be G, GH1, GH2, GH. So what can you tell me about the number of elements in GH versus the number of elements in H? What relation do I have? So what should be true about the size of GH and the size of H? It's the same. Do you think that there's going to be a group homomorphism between GH and H? I'm sorry?
Yeah.
Okay, why?
It's just GH is with H with G multiplied.
Okay, so for group homomorphism, what do you need for group homomorphism?
An identity element in the first. Sorry.
Go all the way to the beginning. A group homomorphism is a map from
G to H.
one group to another.
One group to another.
So we know H is going to be a subgroup of G. So H is a group by itself. Is GH a subset of G? Does GH live inside G? Since everything in H is in big G, by closure, GH is going to be in G. This is going to be a subset of G. It lives inside G, right? Is it a group? Is it a subgroup of G? Is it closed? Is it associative? Does it have inverses? Does it have the identity? It's not clear that this is always going to be a subgroup. We know the identity element is in H. If H1, H2, and H3, if none of them are G inverse, then GH won't contain the identity. So usually this is not going to be a subgroup. Okay. So I don't expect to necessarily have a group homomorphism between the two. So it would be a little bit weird, but they do have the same number of elements. And so here are some properties. So if G is a finite group and H is a subgroup, then the following three things are true. A, every element of G is in some coset of H. Well, given G in G, G equals G times E, which is going to be in G times H, as E is in H. So the first statement isn't that bad. Because H is a subgroup, H contains the identity. So if I want to find a coset that has the element little g, just look at little g times H. So is it possible that an element could be in multiple cosets? Absolutely. But we know if we look at all possible cosets, then you give me any element in G and it's going to definitely be in at least one of them. Okay. Next one is every coset has the same number of elements. Okay. We didn't rigorously prove that, but does that seem reasonable based on what we've done? What do you think?
Yeah.
And so basically there's a nice one-to-one map. You give me something in little g times H, and I can associate the element in G. So this is not too bad. The last one is the more interesting one. If I give you two different G's, then the cosets are either identical or they have nothing in common. Okay? Everybody understand? Once they have one element in common, they must be identical. So let's see. So when you have something like this, a good way of proving it is to basically say, if one of these conditions holds, then clearly one of the conditions holds, and that's not a problem. So if we show that one of the conditions is violated, all we have to do then is show that that implies that the other one holds. So we could either say that there is some element that's in both of them, and show that that implies that they have to be identical. Or we can show that if they're not equal, they can't have anything in common. My feeling is I want to start with some element that's in both and go from that to the same. So assume we have an X in G1H intersect G2H. So we're assuming that it's not empty. If we can show that this implies that the two cosets are the same, then we're done. Because either they have nothing in common, or as soon as they have one element in common, they're identical. What does it mean for X to be in the... Thus, X is in G1H, and X is in G2H. So what would it mean for X to be in G1H? So what does it mean for X to be in G1H? Remember, we said if we had some subgroup H, GH is just multiply on the left by everything in G. So if X is in G times H, what would it mean? Yes. Well, X has to be something in G times H, right? So something in G times H has to be of what form? If X is in GH, then X equals G times the identity, or G times H1, or G times H2, or G times H3 here. Right? That's what it would mean for X to be in G times H. More generally, X is in GH means X is of the form G times what?
HM.
Or just some H for some H in H. We're just unwinding the definition. What does it mean for X to be in little g big H? It means there's some little h in H such that X equals G times H. So going back to our proof, if X is in G1H, we must have an H1 in H with X equals G1H1, just trying to use good notation, and an H2 in H with X equals G2H2. So we know X is G1H1, we know X is G2H2, what can we deduce? Yeah, therefore, G1H1 equals G2H2, or G1 equals G2H2 H1 inverse. Okay. So if I look at G1H, we agree that that's the same as G2H2 H1 inverse. Multiplying big H. And since multiplication is associative, this is going to be the same as G2 H2 H1 inverse H. Because H is a subgroup, what do you think happens if I multiply everything in H by H1 inverse? I am going to get a coset. Which coset do you think I'm going to get? I'm multiplying by H inverse. If life was good, what coset would it be? You take something in H, you multiply it by H inverse lives inside H. So if you take a subgroup and you multiply it, if life were good, can you think of anything that has the same number of elements as H? Which one, though? There's a really nice one. If life was really, really nice, what would be the nicest thing for H inverse H to be? If you could have your wish, what would be the nicest thing? H! It's H! Oops. So this is going to just be H. And then what would H2 times H be? H! And then you would get just G2H. And so the cosets would be the same. We need the following lemma. If H is a subgroup of G and H is an H, then little h times big H equals big H. More generally, it's the same subgroup. More generally, if G is in G, then GG equals G. Because by closure, we know little h times big H is still going to be something in big H. So I could prove this about subgroups, or more generally, if I give you a group and I multiply by some element, I just get all the elements back just shuffled, just in a different order. So here's the proof. Here's the proof. Imagine G times G1 equals G times G2. What could you do if G times G1 equals G times G2? Yeah, that implies G inverse G G1 equals G inverse G G2, therefore G1 equals G2. So what this means is if I take two different elements in big G and multiply them by little g, they go to different things. So the map, fg of x equals gx is injective, is 1-to-1. Two different things are sent to different things. Now, let's show that everything gets hit. Say want G times G1 equals G times something equals some element G tilde. We want to figure out, is there something in G that's sent to G tilde when we multiply on the left by G? Can anybody solve for X? Try X equals. What do you think would work? So when we multiply by G on the left, we want to get G tilde. How can we solve X? What can we do to both sides? We have Gx equals G tilde. How do you solve for X? What do you do? I'm sorry? We can't divide, so what do you have to say instead of divide? Times the inverse, on the left or on the right? Well, we've got Gx equals G tilde. The left, exactly. So that would give us X equals G inverse G tilde, then Gx would be G inverse G tilde would be G tilde. So the map that sends X to Gx is 1-to-1 and onto. It's a bijection. As finite, this means the number of elements in G and the number of elements in little gg is the same. So it's very important that everything is finite here. If we didn't have finiteness, that would not be the case. But because everything is finite, then that is enough to know that the two things have the same size. As an aside, how many of you have ever heard of the Hilbert Hotel? So the Hilbert Hotel is wonderful. It's got infinitely many rooms. One, two, three, blah, blah, blah. It's full. Someone arrives, wants a room. Think, wait a minute, if I've got infinitely many rooms and everything is filled, there's no way to satisfy this person. So you move 1 to 2, you move 2 to 3, you move 3 to 4, and you've just freed up room 1. And so now the person can come in. So you have two different sets of people, and they can both be in the hotel. You can have infinitely many people arrive, and then you move, I'll start with 0. And you would move 0 to 0, 1 to 2, 2 to 4, 3 to 6, and you can free up infinitely many rooms. So as soon as you have infinities, it turns out that there's different levels of infinity. And just because two things have the same level of infinity doesn't mean they have the same elements. And so it's very important here that it's finite. Because there are only finitely many elements, if the two sets have the same number of elements, then it must be the same. Okay, so the big one is Lagrange's theorem. If G is a finite group and H is a subgroup of G, then the number of elements in G is the number of elements in H times the number of distinct cosets of G in H. And hence the order of H divides the order of G. This is one of the big results in group theory. And the proof is following. We agree that G is equal to the union over all G and G of G times H. Because as the identity element is in H, G, E is in GH. So clearly, everything in G is going to be in one of the cosets on the right. And the cosets on the right can't have anything outside of G by closure. So these have to be the same. We all comfortable with that? But we know two cosets are either the same or completely disjoint. So that's the same as saying G, this is the disjoint union. Let's say K goes from 1 to M of G K disjoint union. So we can do that because by what we just proved, two cosets are either exactly the same, so I don't need to have them, or they're completely different. In which case, well, okay, if I don't have you, I need to add you to my group, to my list. Okay. But we know every coset has the same number of elements as every other. And so the size of G is going to be the size of H times K. And we're done. So we've just shown that the size of any subgroup divides the size of the group. Okay. So this has a lot of applications. I'm sorry?
It's the M, I guess, because K.
Oh, yes, you're right. That's the, thank you. Yes. And so this is absolutely wonderful. So why do we care about something like this? If G is in G, then the cyclic group generated by G lives inside G. Thus, as this is a subgroup, the order of G divides the size of big G. Recall, the order of G, little g, is the smallest n such that G to the n is the identity. So we know that no matter what element you give me, some power of it is going to be the identity, and that power has to divide the size of G. Okay, this is nice. There's a particularly useful example. If P is prime, we look at G mod G star, which was 1, 2, double dot, right? So what's the size of that group? How many elements are in that? Minus 1. So if A is in Z mod PZ star, then A to the P minus 1 is congruent to 1 mod P. More generally, if we look at Z mod NZ star, let me do this on a new page. So Z mod NZ star is the elements M from 1 to N relatively prime to N. So for example, Z mod 12 Z star is our favorite. 1, 5, 7, 11. What are the closest ones? That is also seen by C is the number of elements in that set, i.e. number of one, two, three, four. So the size of G of G star is the number of elements in G star is so if A is relatively one, that A is reduces to what we did before. So this is a really nice result. If we look at the clock group under multiplication, if we look at the elements that are relatively prime to n, these are the ones that have a chance of having an inverse. It turns out it's a group. We use the Euclidean algorithm to do this. And you give me any number that's relatively prime to n, then if I raise it to the phi of n, I get 1 mod n. If n is prime, we know what phi of n is. It's just n minus 1. Because if n is prime, then everything from 1 to n minus 1 is going to be relatively prime. All right. I'm not going to go through the stuff about products of groups. I'll let you take a look at that. There's a homomorphism you can do between Z mod MZ and MNZ and the product of two groups. I will leave that for you. There's the structure theorem for finite abelian groups. You would get to this in a second course, not in an introduction, which says that, look, if I give you a complicated group, I can actually break up the group into constituent parts. So if you're going deep in mathematics, this is a result you really want to understand because it tells you if I have a finite abelian group, I know exactly what it looks like. What's the first question you would want to ask after this? So if I give you a finite abelian group, we know what the answer is. We know what it looks like. I'm sorry? So one is to actually do this for certain groups and see how you find them. But here's the answer if the group is finite and abelian. What would you want to know after that? Yeah, if it's not finite, and if it's... So one of my professors at Yale was one of the people who put the final finishes in this 1,000+ multi-year project of what do you do if it's finite but not abelian. And we do have the complete classification. It's involved. I'm not going to go through the projects and inclusions. I want to end with Fermat's little theorem. So we've basically already done this. I don't know why it has put in a dot there, but I can just shift, I think, to white and get rid of it. There we go. Okay. So imagine we have a number a that's relatively prime to n. Then a to the phi of n equals 1. So if n is prime, if n equals a prime p, then that implies a to the p minus 1 is congruent to 1 mod p. Can somebody give me a composite number? 6. Are you sure 6 is composite? Everybody comes together 6 is composite. How do you know that 6 is composite? So you're really comfortable with it. You're not comfortable with 6. Would we all agree that 6 is 2 times 3? If I gave you another number, are you confident about your ability to factor?
What type of number is it?
200 digits. So you were able to show that 6 was composite by giving me its factorization. You're making it really hard for me to disagree with you. You're putting me at the position where I have to say, no, 2 times 3 is not 6. You gave me a constructive proof that 6 is composite. Why is 6 composite? Here it is. Here's a product of 2 numbers. Each one is at least 2. They give me 6. It's composite. If I were to give you a 400-digit number, which had 2 factors, each one of them a prime number with 200 digits, good luck finding that. Six minus 1 is 5. So what is 5 to the 5th mod 6? What's 5 squared? 25, which mod 6 is 1. So 5 to the 5th is 5 squared times 5 squared times 5, which is equivalent to 1 times 1 times 5, which is equivalent to 5 mod 6. As 5 is not equivalent to 1 mod 6, what do we do to that? We just proved that 6 was composite without constructing factors. This should be surprising. If you're talking to a young kid in elementary school, middle school, junior high school, they understand what composite numbers are. They understand if you give them a factorization. We just found a way to show that the number 6 can't be prime. It turns out you can make primality tests on this. And a lot of times, if I give you a composite number, I can find some A such that it's not congruent to 1. Unfortunately, there are a certain class of numbers called the Carmichael numbers that are composite and have the annoying property that they always pass this test. There are very few Carmichael numbers relative to prime numbers. If you pass this test all the time, almost surely you are prime. But it's worth doing some searching and looking at Carmichael numbers. This is just the danger of the necessary versus sufficient. I can use this to find a number that's composite. If it fails the test, if it's not congruent to 1, it is composite. I know 6 is composite, but I could take another composite number, or maybe another A, and get that it does equal 1. That doesn't prove that it's prime. It just proves that it might be prime. So you can try doing this with multiple different choices. And if you do it for many different choices and it always passes, you begin to gain confidence. Maybe it really is prime. It just passed 15 tests. But there are numbers that will pass every single time. So what's frequently done, and this is just wonderful advice, is this is a very fast, easy test to do. So you do this to prune your list of candidates for primes. And if you always pass these tests, or you pass it a sufficient number of times, then you say, okay, I'm now going to pull out the big guns and do the slow, serious test to be absolutely sure. And so you would still need to be able to raise something maybe to the 10 to the 200th power. So at some point, I will have to tell you how to do that quickly. But you can begin to see, I did 5 squared times 5. I could have actually even done this if I wanted to as 5 squared times 5. So we'll talk a little bit more later about how to do these things efficiently. So this is a good place to stop. So we've basically finished chapter 2. So we're going to be moving now into chapter 3.